Hi, I'm Darren Perry, Technical Support Manager for SOPREMA US. And today our objective is to review ASCE 716 and the methods to determine wind design pressures for low slope roofing. So what is ASCE 7? It's the American Society of Civil Engineers design document for calculating loads on buildings and other structures. It's used to calculate design wind pressures, but it's not just for wind loads, and it's not just for roofing. ASCE 7 also is used to calculate other environmental loads such as snow, rain, ice, and seismic loads for buildings and other structures. Now, ASCE 7 was first published in 1988, and the 1998 version of ASCE 7 was included in the 2000 International Building Code. It was the first time the document was included in our building codes here in the U.S. The ASCE 710 version is included in the 2015 International Building Code, and the latest version, the 2018 International Building Code, includes ASCE 716, and that's what we're going to discuss today, is ASCE 716, the latest version. Let's review ASCE 716 to calculate wind design pressures for low slope roofing. The roof design pressure is basically made up of the velocity pressure of wind. When wind flows across terrain and strikes the building, there are basically two components of pressure acting on the roof. There's the internal positive pressure component, the wind that actually gets inside through the building enclosure and basically pressurizes the building from the interior and presses up on the roof. And then there's the component of wind that basically flows over the top of the roof and basically tries to lift up or the suction pressure that pulls up on the roof surface. So you have the combination of the internal positive pressure and the external negative pressure pulling up on the roof. And the combination of that is the design pressure that we'll be calculating using ASCE 716. So basically in ASCE 716 there are two equations with a total of 7 variables to determine your design pressure you're looking for your low slope roofing. The first equation is for the velocity pressure, and we calculate that first using an air constant, 0.00256. That's based on the mass and density of air. Another coefficient in this equation is K sub z, which is an exposure coefficient, and that's related to the surrounding terrain, or often called the ground roughness, and we'll pull that from tables in ASCE 7. Here in table 26.10-1, you find the velocity pressure coefficients for surrounding terrain or your ground roughness B, C, and D, and these exposures are basically they're defined in ASCE 716 for the surrounding terrain of your building. Ground roughness or exposure B would be for dense buildings spaced close together. Ground roughness or exposure C would be more open terrain, such as an airport here. And then exposure D would be buildings within close proximity to open water. So basically what you have here is the coefficient would be, for instance, for a 30-foot high building, 0.7 for exposure B. The wind is broken up and is more turbulent as it flows around and over tightly spaced buildings. That coefficient goes up slightly as the wind becomes more laminar as it flows over open ground, and it's even higher still, inducing even higher pressures as the wind blows over open body water. It's more laminar and smooth and can create a higher pressure. Thus, it has the higher exposure coefficient. The next variable in our equation for velocity pressure is K sub zt, and K sub zt is a topographic factor. It's usually going to be 1, just 1.0 for uniform open terrain or just uniform terrain. Now, if your building happens to sit up on a hilltop, you would calculate your K sub ZT coefficient, or if it were to set up on an escarpment, where the wind would come across to, say, open uniform terrain and then be compressed by a hill or escarpment, the wind would speed up. And so you have to account for that by calculating this topographic factor. But in most cases for uniform terrain, it's going to be just 1.0. K sub D is a wind directionality factor, and for roofs that's going to be simple. It's just 0.85. So that variable is pulled from table 26.6-1. And basically all it says is the wind is random, and you've got about an 85% chance that the wind will all be coming from any one given direction, and an 85% probability that the maximum pressure coefficient will occur for any given wind direction. So it's just reducing the probability that wind is all going to come from the same direction and have this the same effect. There's a new factor included here in ASCE 716. It's the ground elevation factor, K sub E. And basically this adjusts the pressure based on the height above sea level. So for buildings that are at sea level, it's going to be 1.0, and you can always assume 1.0 and be conservative. But if your building is located in a higher elevation, you can actually calculate this K sub E, or you can simply pull it from the table here and interpolate. For example, let's say your building's in Denver, Colorado. That's a mile-high city. It's let's say it's 5,280 feet above sea level. Your K sub E would be 0.82. And this is relevant for buildings that are located in higher elevations because it's actually going to reduce your velocity pressure and reduce the pressure acting on your roof. So for instance, in Denver, you could actually reduce your velocity pressure by a factor of 0.82. Okay, your velocity, your wind speed. In ASCE 716, you're going to pull that from maps. And in ASCE 716, there are 4 risk category maps. Each map corresponds to the risk category for that building. For instance, our risk category 1, the definition is included here in ASCE 716. That would be a low risk of human life. And that map is basically includes a 300-year MRI or return period, and that equates to an annual probability of 1 over 300, or about a 0.33% chance annually that this wind speed would occur. Risk category 2, these are buildings that are basically the risk categories, all buildings except for risk category 1, 3, and 4, which is pretty broad. That map includes a 700-year return period, or a 0.14% annual probability that this wind speed might occur. The risk category 3, the definition here is a little broader, and the discussions here are more around buildings that represent a substantial risk to human life. And you can read through here more specifically some examples. But that map includes less probability. It's got an annual probability of 0.06, a 1,700-year mean recurrence interval for this wind speed, so more conservative, and would be chosen for more higher risk buildings or more substantial buildings that risk to human life. Risk category 4 would be essential facilities, and they're defined here as well. 3,000-year return period, 1 over 3,000, a 0.033 annual probability, so very low probability that these winds would ever occur, but they would be used for more essential facilities, higher wind speeds. The risk category for buildings should be selected by for the building use itself, the building occupancy. You want to refer to your local jurisdictional codes, consult with the building owner and the designer of record to determine the appropriate risk category and wind speed for your building. So now we've selected, or we've found all the variables for the velocity pressure equation, so you can calculate the velocity pressure, the pressure induced by a wind simply blowing across the terrain before it actually hits our building. So now once we have that velocity pressure, let's calculate the actual design pressure. That's what we're looking for. That's our goal. We're looking for the design pressure actually trying to blow the roof off the building, and we want to try to find that pressure. So we plug in the velocity pressure into this equation. And now we need to find a few other variables. We're looking for the G, C sub P, and that's the external pressure coefficients. And basically there, you may be familiar with this. This is your coefficients for the field of the roof, for the perimeter and the corners, that vary based on the roof geometry, or the roof shape and slope and things like that. So we're going to look for those tables in ASCE 716. There are big changes between ASCE 710 and ASCE 716 for low slope roofing. For example, for typical low slope roofs, we refer to figure 30.3-2A in ASCE 716. And for low slopes, again, we're talking about slopes less than 7 degrees with a pitch less than 1.5 inches and 12. For below 60-foot high roofs, there's some big changes here. We have some changes with the external pressure coefficients themselves, but the really big changes are the roof zones, what we used to refer to as field perimeter and corner zones, or zones 1 prime, 1, 2, and 3 now. And the big change really is the size of these roof zones. Previously in ASCE 710, the roof zones were defined by the lesser of 10% of the width or 40% of the roof height. Now it's just 60% of the height. So before in ASCE 710, usually your perimeter and corners were relatively small because they were the lesser of 10% of the width or 40% of the height. Now it's simply 60% of the height. So these can get rather large. Let's take a closer look at this figure in ASCE 716 for the roof zones. We'll also look a little closer at the external pressure coefficients for each roof zone. So for zone 1 prime, for example, for a low slope roof, the field of the roof, the pressure coefficient is -0.9. It's actually lower than 1. So there is some benefit here for the zone 1 prime. For zone 1, the width of this area is 0.6 times the height. So for example, if you had a 30-foot high building, that zone or that area would be 18 foot wide. And the pressure coefficient is -1.7. So that's really a lot higher than before in this area of the building. The exterior perimeter zone, zone 2, the coefficient, the external pressure coefficient is -2.3, which is a bit higher than before in ASCE 710, which was just -1.8. And then in the corner, at the corner zone, the pressure coefficient is -3.2, which is a bit higher than before. And its shape is an L shape, whereas before it was simply a square, which gets a bit more complicated too. Now for other building shapes, roof slopes, there are several other figures in ASCE 716, but today we're just going to focus on your basic low slope roofing. So we're really not going to get into all these other figures, but they are there and work basically the same, use the same methodology to determine your external pressure coefficients for your roof. Okay, And also, I'd like to point out for low slope roofs higher than 60 foot, the figure here in ASCE 716 is the same as it was in ASCE 710. No changes there, but you would choose your coefficients in your roof zone size and shape using the figure here in ASCE 716. Okay, now for the last variable to find here to determine our design pressure, we're going to look for the internal pressure coefficient. And that's the basically the coefficient that determines how much wind gets in through the building enclosure and tries to pressurize the building from the interior and push or blow the roof off from the interior of the building. So that's it's very simple. It's you pull that from a table in ASCE 716. The GC, so PI, the internal pressure coefficient, is chosen from this table, and you basically got three to choose from. For enclosed buildings, and for now a new term, partially open building, the coefficient is a positive 0.18. And that's going to be your typical building with uniform openings around the entire building enclosure. So for most buildings, that's going to be what you would choose. Now, it's important to understand what a partially enclosed building is, and that is defined here in ASCE 716. That would be a building that has a dominant opening on one side where wind can get into the building enclosure and pressurize the building and without having equalized pressure for the building. It's defined here in ASCE 716, but if you have these conditions, if these conditions are met, then the internal pressure coefficient would be a positive 0.55. An example of that would be, say, an airport hangar where a wind can blow through one opening and pressurize the building, and the wind pressure cannot be equalized through other openings and other walls of the building. An open building would be an example of an open building would be a building where wind would just simply blow through and would not build up any internal pressure. Say a pole barn that would just be open and allow wind to blow through. The coefficient will be just 0. So now we've actually found all 7 of our variables used to find the design pressure for a low slope roofing. We'll review those real quickly here. The first one in our sets of variables for the velocity pressure first was K sub Z, and that's the same as it was before in ASCE 710. You pull that from a table. That's your velocity pressure coefficient. Your topographic factor is usually going to be 1.0 for uniform terrain surrounding a building. Wind directionality factor for roofs is always going to be a 0.85. Your elevation factor, your ground elevation factor is based on height above sea level. The default is going to be 1.0, but you can use that to reduce your pressure if you're in high elevations in the U.S. Your basic wind speed is pulled from a risk category wind speed map. There are 4 maps now in ASCE 716. Before in ASCE 710 there are only 3. A pretty simple process there. So once you have all those variables, you calculate your velocity pressure, the pressure induced by wind simply just blowing across the terrain. And now we select or we plug that variable into our equation for the design pressure, and that's what we're really looking for here today. We're looking for the pressure acting on our building roof. And our variables there are the external pressure coefficients, the coefficients that are relevant to the actual building roof, the field area and your perimeter areas, your corner areas. And again, in ASCE 716, we have 4 zones, the 1 prime, the 1, the 2, and 3 zone. And then we plug in our internal pressure coefficients, the same as they were before in ASCE 710. And you would pull that from a table. There's some new guidance for you in ASCE 716. Basically, you have a enclosed building and a partially enclosed building scenario to look out for. Then once we plug in all these variables, now we can come up with our ultimate design pressure. Now, it's important to know that the ultimate design pressure is typically not what you're going to use to select low slope roofing. For low slope roofing selection, you're looking for the allowable stress design pressure, and to obtain that, you're going to multiply this ultimate design pressure by a load reduction factor of 0.6. So once you calculate your ultimate design pressure, multiply that by 0.6, and you're going to come up with what's called the allowable stress design, or ASD, pressure. That's the pressure you're going to use. That's the design pressure you're going to use to select your roofing system that's been tested by a manufacturer or in a third-party laboratory. And that's going to be what you're going to use to meet the International Building Code and other jurisdictional codes for low-slope roofing. So for more information related to this topic, refer to the video description indicated below. Thank you.